Today we're going to talk about algebra tiles and how we can use them to build algebraic expressions. So we're going to make some observations about the algebra tiles, ask some questions about the algebra tiles, and hopefully answer some questions about the algebra tiles. So if you'll take a few seconds to take a look at the algebra tiles over here to the left, and I'd like you to think about some observations. Maybe you noticed that there are different shapes of tiles, that there are multiple colors, and that there are 3 different sized red tiles. Those are great observations. Let's take a few seconds now to think about some questions about the algebra tiles. Why are they different shapes? Why are they different colors? And what are they for? Those are great questions. We're going to start by making some observations about the yellow tile here. What do you think the yellow tile represents? So when experimenting with the actual physical algebra tiles, we discovered that the side lengths of the actual algebra tiles are 1 centimeter by 1 centimeter. Well, 1 centimeter by 1 centimeter is 1 square centimeter. This has the value of 1. Let's take a look at this congruent square. It is also the same size and shape as the yellow, but it's red. This is going to represent -1. Now we're going to take a look at the green rectangle. So I'm thinking that this yellow, there's something that the yellow and the green have in common. Notice the side length of the yellow is also the same as the width of the rectangle. So the width of this rectangle is 1, and the length, I don't know yet. I'm going to see if I can use the yellows to figure out the value of this green rectangle. So there's 1 by 1, 1 by 2, 1 by 3, 1 by 4. But I've got these little gaps in here. I better kind of line that up here and see if I can get that lined up a little bit nicer. I don't think it's exact since there's little spaces there. Yeah, okay, so 1, 2, 3, 4, 5. The length isn't quite 5. Let's see if I bring down 6. Well, it's not going to be a 1 by 6 either. So you know what? I really don't know the exact length of this, this green rectangle. It's 1 by an unknown. We're going to call that unknown x. And 1 by x, 1 times x is x. So we're going to call this the variable x. Let's take a look at the red. It's congruent figure to the green, same shape and size as the green. This is going to be -x. Let's look at the blue square. I'm wondering if I can use these rectangles here to figure out the value of this blue square. And I think I can because I'm noticing they share a side length, it looks like. They have that in common. So I'm going to bring this green x down here. And I'm noticing that the side length of the green rectangle is the same as the side of one of these this blue square here. So I'm going to see if I can use these x's to figure out the value of the big blue square. 1x, 2x, 3x, 4x. It's not quite 4x. 5x? No, that didn't work either. But I still think we're onto something with the idea of the x value. I wonder if we can do let's do some rotating here. We're going to bring down another green rectangle, another x. I'm going to set those up here. Now this reminds me of an area model that we used to use for multiplication. I've seen that a lot in our 5th grade classrooms. So let's say we had set up an area model multiplication problem and this value was 10 and this value was 10. Well, we would call this 100 because 10 times 10 is 100. But in this case, we know that this green is x and this green is x. So x times x is what? What's another way to say x times x? Well, if you said x squared, x to the second power, you are exactly right. So I'm going to go to my Equatio here. I just clicked on the Equatio icon. It's an extension, and it's great. If you don't have it, I highly recommend you download that. And we're going to go ahead and enter x squared here. And you have to be kind of quick. It doesn't take long before it pops it into the little text box there. So I'm going to go ahead and insert x squared. Let's see if we can enlarge it here because it looks pretty small. There we go. There's x squared. Let's put that right here. All right. Now, how about taking a look at, we're going to group these here real quick. Let's take a look at this red square here. It is congruent to the blue, same size and shape as x squared, but it's red. So we are looking at a negative x squared. All right. So now we have identified the values of our algebra tiles. Positive 1, negative 1, positive x, positive x squared, and negative x squared. We're going to go ahead and build some algebraic expressions now using our algebra tiles. Come back to Equatio. And I'd like to start with x plus 4. We'll enlarge that a little bit here. X plus 4. One group of x plus 4 groups of 1. 1, 2, 3, 4. All right. Now we're going to build 2x plus 4. So in the first expression we looked at, we just had x plus 4. You heard me say one group of x plus 4. Well, we just had one x. So our coefficient, even though we can't see a 1 there, it's 1. Let's take a look at this one. We have 2x. The coefficient 2 tells us how many groups of x. 2 groups of x plus 4 groups of 1. So let's go ahead and build that. 1 group of x, 2 groups of x, and 4 groups of 1. 1, 2, 3, 4. Okay, we're going to take a look at another expression. This time we're going to look at 2 groups of x plus 4. So let's take a look and compare the two expressions here. Here we have 2 groups of x plus 4 groups of 1. When reading this expression, we would actually read it as 2 groups of whatever is inside the parentheses. So this is actually 2 groups of x plus 4. So I could start by building 1 group of x plus 4 groups of 1. Because the coefficient is telling me to build two groups of whatever is inside the parentheses, and what's inside the parentheses is x plus 4, then I can go ahead and build a second group of x plus 4. So let's compare the two models here. What do you notice? Well, I notice that 2x plus 4 shows two groups of x and only one group of 4. But two groups of x plus 4 shows two groups of x and two groups of 4. We're going to take a look at another series of algebraic expressions. So we're going to start with x squared minus 3. There we go. Put this up here at the top of my Google Drawing. All right, and we can't see the coefficient 1 here, but it is understood that this is one group of x squared. So I'm going to go ahead and bring over one group of x squared, and then I need three negative ones. X squared minus 1, minus 2, minus 3. X squared minus 3. All right. Now I want to look at 2x squared minus 3. So this time we see the coefficient 2. 2 what? Two groups of x squared. So I'm going to bring over one group of x squared, two groups of x squared, and three negative ones. 2x squared minus 1, 2x squared minus 2, and 2x squared minus 3. All right, let's take a look at one more example. This one has 2, then parentheses, and inside the parentheses is x squared minus 3. How do you think we would read that? I'm going to read this as two groups of x squared minus 3. So I've already seen what one group of x squared minus 3 looks like. This is asking me to build two groups of x squared minus 3. So I'm going to use my algebra tiles to build a representation of two groups of x squared minus 3. There's x squared minus 1. Minus 2 minus 3. X squared minus 3. Now I need to build two groups of x squared minus 3. Go ahead and create another group of x squared minus 3. And let's take a look at what we've got here. Let's see how these compare. So originally we had one group of x squared minus 3, one group of x squared, and one group of negative 3. Then we went to two groups of x squared, one group of x squared, two groups of x squared, and negative 3. And then finally, we ended up with two groups of x squared minus 3. There's two groups of x squared and two groups of negative 3.